Imagine a world where consciousness transcends the fragile confines of flesh and bone. A world where memories, thoughts, and identity could be preserved not just in stories or photographs, but as a living, breathing digital entity. For centuries, this has been the stuff of science fiction, a distant dream whispered among futurists and philosophers. But what if that dream has already begun to take its first, tentative steps towards reality? What if, for the very first time, a brain's entire, functioning neural network was meticulously mapped, neuron by neuron, synapse by synapse, and then uploaded into a computer? The implications are profound, shattering our understanding of life, mind, and the very essence of what it means to exist. The concept of transferring one's mind into a machine has captivated humanity across millennia. From ancient myths of souls migrating to new forms, to Mary Shelley's Frankenstein, and the countless dystopian and utopian visions of cybernetic futures, the desire to overcome biological limitations is deeply ingrained. But the leap from philosophical musing to scientific endeavor required a paradigm shift. For decades, neuroscientists and computer engineers have grappled with the sheer complexity of the human brain, an organ containing roughly 86 billion neurons, each forming thousands of connections. To upload it would mean not just scanning its structure, but understanding its dynamic processes, its electrochemical language, and replicating it digitally. It seemed an insurmountable task, until we decided to start small. The first critical step towards digital consciousness is creating a complete map of a brain's wiring diagram, its connectome. Think of it as the ultimate circuit board schematic. For a human, this is a challenge of astronomical proportions, requiring resolution down to the nanoscale. But nature offers simpler models, organisms whose entire nervous systems are significantly less complex, yet still capable of intricate behaviors. Enter Habdates elegans, a tiny, transparent nematode worm just about a millimeter long. It's no particularly glamorous, but it possesses a fixed, well-documented neural network. A male C. elegans has exactly 385 neurons, a hermaphrodite 302. These neurons, along with their precise synaptic connections, were the target of an unprecedented mapping effort. In the late 1980s, a team led by Dr. John White and Dr. Sidney Brenner embarked on what would become a monumental achievement, mapping every single neuron and synapse in a C. elegans hermaphrodite. This wasn't a quick scan, it was a painstaking, manual process. The worm was first preserved and then cut into thousands of ultra-thin slices, each just tens of nanometers thick. Each slice was then photographed using an electron microscope, generating an enormous library of images. Researchers then had to manually trace each neuron and its connections across these thousands of images, often spending years on a single nerve bundle. Imagine piecing together a three-dimensional jigsaw puzzle where each piece is microscopic and you have no reference image. This labor-intensive process, while incredibly slow, yielded the first complete connectome of any organism. It was a digital blueprint, but still a static one. With the connectome finally mapped, the next audacious step was to bring it to life. This is where the Open Worm Project, an international open-source initiative, took the baton. Their goal was not just to store the map, but to simulate the worm's entire nervous system in a virtual environment. Each of the 302 neurons was modeled computationally, including their electrical properties, how they respond to stimuli, and how they transmit signals across synapses. These models were based on decades of neurobiological research. To truly test the upload, the digital brain needed a body. The team created a virtual C. elegans body, complete with simulated muscles, and a physics engine that allowed it to move and interact with its environment. The result was groundbreaking. When the simulated brain was connected to the virtual body, it began to exhibit behaviors characteristic of a real C. elegans. It could navigate simple environments, respond to virtual touch, and even show rudimentary forms of learning. It wasn't just a map, it was a fun, cautional, digital recreation of a living brain, uploaded and running in a computer. The successful simulation of the C. elegans brain, while seemingly modest, represents a monumental leap in neuroscience and artificial intelligence. It validated the idea that a complete neural map can be functionally replicated, opening doors to understanding how even simple brains generate complex behaviors. For neuroscientists, this provides an unprecedented tool to study brain disorders, test hypotheses about neural circuits, and understand the fundamental principles of consciousness without the ethical constraints of animal experimentation. For AI, it offers a bio-inspired blueprint. Imagine building artificial intelligences not just on abstract algorithms, but on the proven architecture of life itself. The C. elegans project serves as a foundational step towards more sophisticated, biologically plausible AI. The journey to mapping and uploading a human brain remains incredibly distant, fraught with technological, ethical, and philosophical challenges. The C. elegans has 302 neurons, a human has billions. But the precedent has been set. The first brain has been mapped, uploaded, and brought to life in the digital realm. The questions it raises are profound. What is consciousness? What defines identity? Indeed, as we continue to push these boundaries, are we merely observers, or creators of a new form of life? From the humble nematode worm, we have learned that the mind, in its most basic form, can indeed be translated into code, its intricate dance of neurons replayed on a silicon stage. This isn't just a scientific curiosity, it's a testament to humanity's relentless pursuit of knowledge, a whisper of a future where the lines between biology and technology blur. The journey has just begun, and the ultimate destination remains shrouded in mystery, yet illuminated by the incredible potential of a digital, defined future. What further marvels await us as we continue to unlock the deepest secrets of the brain? Only time and continued scientific endeavor will tell. Thank you for watching our video. Don't forget to like and subscribe. We value your thoughts greatly. Let us know in the comments.